It's a great honor to be here. It's a great honor to get to dwell on the deep influence of Dennis Sullivan in my own life and in topology, and to get to try to convey to you a little bit about the mathematics he did and about what it felt like to learn about this over the years. So today, I'm going to tell you the story of the great wild manifold rodeo. And but before we get there, we have to go through some other stuff. So, can I turn this light off somehow? Here, is that okay? Okay, thank you. I'm sorry. So whenever you start a great story, it always, like if you're Frodo and Merry and Pippin and you're going to go off into the with the great ring and all that, it always takes place in sort of in a situation where the legendary exploits of the people that came before you are all that anyone's talking about. So maybe you run into Aragorn, son of Arathorn, and then you have to hear a whole bunch of stuff about Arathorn before you really get to know what Aragorn has done. And it's like that in math. I mean, when I came into math, the sort of work of Dennis and his cohort was the stuff of legends. And it's stuff that revolutionized our thinking about geometry and topology and what these ideas mean. And these are just some of the names that are involved in this story. But the world of geometry, what we think about geometry, how we understand how to use geometry, went through a radical revolution starting in the late 1800s and moving up into about the 1970s. So I'll just let this finish. This work of all of these people kind of culminated in the late 60s and early 70s in the phenomenal work of Dennis Sullivan. So, before I can get to the legend and the great wild manifold rodeo, we need to just stop and think about what classical geometry is. And so what I've done here is I've just put up some images from classical geometry, and just to get everybody thinking right, I'm just going to let them scroll by in silence and just look at them and watch them and just note, what you think about when you see those images, because that's really the beginning place. It's the first theory of geometry, and it's where all this stuff grows from. So I'll just let you watch this for a minute. I never get tired of looking at those kind of pictures. I mean, we learn that stuff as a child, and we learn analytical reasoning. We learn, we see comic books. We see the world through those forms. We see theories of nature written in this language of classical geometry. And if I had to step back, I mean, the numbers themselves are there in Euclid's geometry. And if I had to step back and just say and think about what was classical geometry about, it's probably just a study of pure abstract shapes. Shape is a word that doesn't really have any meaning, and it's a way of starting to codify shapes that we would look at: triangles, squares, ellipses, and things like that. And also, these shapes, seem to be something we use to describe the fundamentals of the universe we live in. And the Greeks had a much more ambitious way of saying that. They described this in terms of a Platonic ideal. There were two principles that nature is described in terms of these pure forms, and these pure forms themselves, they live in another world, a world of abstract. They occupy their own universe. So one of the things, if you stop and think about this, this is probably arguing that the Greeks advocated for the multiverse, or at least they had two universes, one for the equilateral triangle and then the one where we live. So this idea of these ideal shapes living in one universe, us dwelling in another, is an articulation of the multiverse, and that was supposed to be a hilarious joke that I stole from a book of Neil Stephenson. So this is a useful way, though, thinking about this multiverse thing is a useful way of locating a number of the mathematical structures I want to talk about. So that was geometry for a long time, just these abstract shapes. And when you look back on it, those shapes were just described by linear and quadratic equations. And after Descartes and after the mathematicians got working, new shapes emerged that were studied as the solutions to equations. And these took hold in the mid-1800s, especially. Here's an equation that's of degree 4, and this is an equation for the famous Kummer surface. This is another sort of stuff of legends. Most of us, we go into the math department and we walk down, and there are these cabinets full of these plaster models, and this is one of them, the Kummer surface, and it's sort of mysterious what they're about. You have to there's not a page of explanation there. You have to do something. You have to learn something to understand these models. These models, they were made by Schiller. There's a quote here, Schiller, who, I'm sorry, I've got to find it. Martin Schiller, who made these were he sold these to math departments all over the world. And in 1932, he wrote a letter to the Göttingen Mathematical Institute informing that he was suspending production of these mathematical models because visualization had lost its significance and a new era of mathematical formalism led by Nicolas Bourbaki was coming in and replacing this kind of visualization of math. So this affects geometry. Oh, yeah. So you can find all of these scans of these classical models at this website. And this sort of move to abstraction affected the way we think about geometry. In fact, the idea that geometry is studying shapes is really tied to visualization. So there's another influence in what we want to think of as geometry and space, and it comes from thinking about geometrical things in a different way. So in Euclid's geometry, a point is defined to be something vague. It's something which has no extent. But the beauty of that is that a point can stand, it can be a proxy for anything else. And back in classical Euclidean geometry, there's a famous, I wonder, does this have a laser pointer? Wait, does this? No? A pointer? No? A lightsaber? Oh, the mouse? Huh, weird. Okay, so here's this yellow circle, right? And then if I look at this point, I can draw circles that are, when they meet this, they meet it at a right angle. And the cool theorem from classical geometry is that all those circles have a center. They're the centers of all those circles, that's those blue dots. They line up on another line. And so I can think of that points of that blue line not as little points. I can envision them as circles themselves. So this is a moduli space of circles, or in the language of classical geometry, it's a pencil of circles. But we're looking at points in a line, but we're thinking of it as a family of other objects. So that's a very ancient version. In mechanical engineering, there's a study of something called a 4-bar linkage. So a 4-bar linkage consists of 4 bars linked. And so down here is one of them. Those are fixed. and then these other 3 bars are free to move. And so there's only so many positions that can occupy. So let me just see if I forgot what the next slide is going to do. Yeah, so you can see as I move around that loop down there, that corresponds to positions of the 4-bar linkage. So the positions of the 4-bar linkage are described in terms of geometry by 2 circles. Well, they're not actually circles, and we wouldn't care if they were really circles. What we care is that they're round and that they reflect the periodic motion that we just described. That particular 4-bar linkage, I can't move it to, it has 2 different components. I can't, if it's in this position, I can't move it up to the other position, which is when it's above that. So why isn't that playing? All right, so there it is in the other component. So if we're thinking of our points as being a configuration of the 4-bar linkage, then those points, what we care about in terms of that space is its shape in some vague sense, that it reflects periodic motion, and that it had 2 separate components. So Okay, so out of this analysis comes some really important concepts in geometry. And the first is something I'll call proximity, just because that means something more to us than the word topology, which is what's used in mathematics. So the idea of proximity is that if I move something in this parameter space, or this moduli space, a little bit, that corresponds to a small motion of the 4-bar linkage. So one idea here is that geometry may not have to do with shapes, but one of the things it has to express is proximity, or topology. Sorry, I can't... Okay, yeah, sorry, I didn't see that changed. So another thing is that the degrees of freedom in your model don't suddenly get restricted at some point. If at every point you had 2 directions of motion, well, I could build something that just hit a dead end, but generically, I would want to look at systems. It would make sense to ask for systems that have the same number of degrees of freedom at every point. And so when we look at that in mathematics, that's something we call a manifold. So that's a special kind of geometry, a special kind of abstract space where there's the same number of degrees of freedom at every point. And if you want to think of it in terms of the configurations of some mechanical system, you're saying the system doesn't just hit dead ends at some point. And another notion is smoothness. So that 4-bar linkage I drew, it moved smoothly at every point. It didn't go and stop, and then something had to move into a different position before it could continue. If I had built it well and it was going to be a beautiful mechanical device, it would move smoothly. And we use that word smooth to describe another geometric structure over in that circle, that piece of the configuration space that corresponds to smooth motion when I think of it as a mechanical system. Okay, so those are right. So those are 3 notions. I'm sorry. So it's funny. You learn math from all kinds of places and all kinds of people. And I learned about the 4-bar linkage from this artist, Anne Lilly, who makes these amazing kinetic sculptures. And I wanted just to show you a piece of her work, just to show you something more beautiful than the 4-bar linkage that I had. And it's, here you can see the motion is very smooth. I'm not quite sure if that plate is actually fastened to the base or if there's 1 or 2 degrees of freedom. But you can see in the parameter space is probably very simple, but the motion being described is extremely elaborate. So this is a... let that finish. I also learned from Anne another legend, which is about four-bar linkages. So there was a book called The Analysis of the Four-Bar Linkage by Hones and Nelson that was written in the 1950s. And some people have copies of it, and you can't find it anywhere. It's not on any illegal download site on the internet. It's nowhere to be found. It's just another legendary thing in mathematics. Okay, so we started with geometry. We thought of different ways that space and things might correspond to stuff. And when we thought of it in terms of spaces corresponding to configurations of other systems, three concepts have emerged. One, which I called proximity, that when you move something a little bit, the other part moves a little bit. One called manifold, which means that the number of degrees of freedom don't change as you move from point to point. And the other, which was called smoothness, that corresponded to a smoothly operating system. Now, the notion of proximity actually splits into two pieces. And one way to think about that is to imagine where we have something in nature. Now, I was trying to sort of make that look like a grassy field, but the program that mapped it onto the surface I drew made it look like, I don't know, the bottom of a carpet or something. So I apologize for how unappealing that looks. But let's imagine that was something in nature, something fuzzy and very irregular. And when we look at that, but nevertheless, if we were small enough that we were walking through that, we would know when we had moved a little bit or when we had moved a lot. And so underlying this in some other multiverse is an abstract topological form that merely expresses the proximity between the positions in that scene. Now that's very idealized, and it requires specifying an infinite amount of information, and there's probably only a finite amount of information in that piece of landscape. And if we actually went to survey it, we would mark a bunch of points, and we would identify some positions of all of these points. There'd be finitely many points, and we would have some network of information that would represent this shape. And that network of information appeared in Dennis's talk, and it was introduced by Poincaré, and this is what we call a triangulation, or I'm going to call this a piecewise linear notion of proximity. So a graph like that, with all of its information, would represent when points are near to each other, and that other kind of milky-looking abstract thing is also a representation of that. So if I put all these together, so there's two notions. Proximity splits into two notions. One is topological proximity, and the other is piecewise linear proximity. And as I said before, you can think of piecewise linear as what you would get if you did an actual land survey of the various positions in whatever space you're looking at. That space might be a parameter space for some other structure, in which case you'd be plotting different attributes of the position of your system, but that's what that would... But anyways, these don't have to look geometric to us. Now, it's worth noting dates here. So I brought in these notions. The notion of smoothness combined with manifolds, this is, I guess, a little out of order. Sort of the PL, the triangulated notion of proximity, was introduced by Poincaré in the 1890s and developed further by Dane and Haggard in 1907. The notion of just topology, just proximity without any of these other attributes, wasn't formulated clearly until 1914, and the notion of smoothness wasn't really formulated clearly until the 1930s. So these are, in the scheme of things, relatively recent ideas, and the contributions I was talking about at the beginning, those are taking place in the 1960s and 70s. So it's not long. I mean, mathematicians have been able to ask these hard questions or identify these different notions of geometry, and the relationships between them didn't really the unclear relationships between them became clear in a remarkably short amount of time. All right, so let's step back. I'm going to just organize this in this multiverse thing. So down here at the bottom, we've got this fuzzy green thing, which is the universe we live in. Here we have the strand in the multiverse where there's triangles and ellipses and all of the Greek kind of geometry. And we sort of studied, thinking of spaces as moduli spaces or configuration spaces of mechanical systems led to different ideas about different multiverses, different abstract mathematical ways of thinking about geometry. So there was this notion of proximity, there were two kinds of that, and there was this notion of smoothness and manifold, and if I combine all those together, I get 5 notions above. There's sort of the world of manifolds, which, if you want, is that the world of topological spaces and piecewise linear spaces have instantiations in the world of manifolds that can instantiate in Platonic forms that could instantiate in our universe. So these are the structures that I've introduced, and I've given some graphic examples of what they look like. And a fundamental question occurs right away, and that is, are these really different? Let's start up at the top, is the topological notion of proximity really different, or is it the same as the approximation you would get to the notion of proximity by a survey? So are topological spaces and piecewise linear spaces more or less the same thing? And then there's the same question for manifolds, where there's a further notion of smoothness. So are smooth manifolds really the same thing as topological manifolds, and are those really the same thing as piecewise linear manifolds? So these questions, they come under the name of the Hauptvermutung, or that's one question. That's going to be my proxy for all of these questions. And the Hauptvermutung was, it really says what's the relationship between topological and piecewise linear, or between that milky landscape and the one that was constructed from a survey out of triangulations. So the Hauptvermutung was formulated in 1908 separately by Steinitz and Tietze, and it conjectured that these are essentially the same, that they're the same notion. This was very natural, and it was early on shown to be true in dimensions 1 and 2. It's interesting to notice the dates, right? This is formulated in 1908, but these notions, like the notion of a space, wasn't really clearly formulated till 1914. So this is an amazing period. It's sort of it's just an amazing period in math, where sort of the intuitions and the ideas are outpacing even the ability to formulate abstract structures that properly describe them. All right, so as we learned in the introduction, sort of the first surprising answer was that it was due to Milner, an earlier Abel Prize winner, in 1961, that said there are inequivalent PL spaces that are topologically equivalent. So you could do 2 surveys of the same landscape. So you could start with a landscape, you could do 2 different surveys, get 2 different triangulations, and there's no way that you could do a finer, more careful survey that reproduced both of them. So this is a shocking thing, and it goes against it's not true in dimension 2, so it goes against all of our intuitions. And anyway, but Milner shockingly produced this example. So this wasn't part of the Hauptvermutung, and it was an earlier contribution, but he showed that the notion of smooth and topological manifolds are different by producing two different smooth manifolds that had the same underlying topological manifold. So that's hard to envision, and I'm not going to try to explain it today. But anyway, this is so already in the 50s, though, this sort of the distinctions between these different classes of geometric objects are emerging. So another one, a famous one, was Curvaire, who showed in dimension 10 that there's a PL manifold with no smooth structure. So the notions of smoothness is radically different. Smoothness is not a consequence of proximity, no matter how you want to think about it. No matter how you describe proximity, whether you describe it in topologically or in terms of piecewise linear things. And so the big thing, the sort of tale of the great wild manifold rodeo, is that Sullivan showed that the manifold Hauptvermutung is almost always true. There's one problem you have to deal with, and then you can often arrange that this obstruction doesn't appear. And this Sullivan's method was just a spectacular analysis of the spaces controlling the surgery of manifolds. So I need to go a little further in the math before I can get to the famous story of this, the famous legend of this manifold rodeo. So when we studied in that picture of the family of circles, right, those circles were undergoing a transformation. They were getting bigger or smaller and remaining perpendicular to a given circle. When we looked at the motion of the four-bar linkage, the four-bar linkage it could just transform, right? I couldn't change the lengths of the bars. It could only just transform by moving as a mechanical system. But what if we're not studying that? We're studying this abstract notion of proximity or piecewise linear or something like that. If I wanted to take the moduli of all those, if I wanted a space that described all of those, then what are the motions that those kind of objects would undergo? And that motion is something that's called surgery. So the next kind of geometry I need to talk about is sort of homotopy theory. So to get an idea, I need to produce a family, a changing topological space, or a changing situation in geometry where I'm looking at proximity or something like that. And so let's go back to this period right after the Greeks, where we're imagining that we are looking at the solutions to some equations. Maybe I have a function f of x, and I'm looking for the solutions to the equation f of x equals y1. And in this case, these two green circles form that solution space. Well, I could study the same function by looking at f of x equals y2. And as these points vary, y1 and y1 moves down to y2, that solution space varies, and it undergoes some kind of transformation. And so that transformation is called a surgery. The two circles at the top are related to the one at the bottom by surgery. Makes more of an impression to, So the other thing about surgery is that so remember when we studied the moduli space of the four-bar linkage, the pieces looked round. We call them circles, but it didn't really make sense to ask that they be perfectly round. They weren't capturing any idea like that. So we studied them just through this lens of proximity or smoothness or manifold. And when you're studying now up at this level, the surgery is controlled by something called a homotopy type, something that merely exists up to deformation. And the homotopy type controlling surgery has this name. It's called G mod PL. I'm not going to explain that name, but I'll just use that as a reference for the thing controlling surgery. And, in math, when you step back, when there's some system you're describing and you go, I want to understand the space of all configurations of that mathematical system, then you're working with some new mathematical object, and it's like you're stepping into a cockpit or something, and you have a whole bunch of controls and you're moving those controls around maybe it's a joystick moving around in some piece of a sphere or some other configuration space. And as you move these controls, the thing you're studying starts undergoing its transformations. And as a mathematician, your experience of it is a little bit like getting into a car, going, all right, let's see what this knob does. Let's see what this can do. Or it's like getting on a horse and saying, what does pulling on these reins do, or what happens if I kick the horse? You get a feel for how these work. And getting a feel for a homotopy type is a really unusual thing, and it took many, many years for people to really get a feel for how to work with homotopy types. And Dennis's results, Dennis's theory here was a huge influence in this. Sorry, that was a bit of an aside. I want to talk a little bit more about surgery. So I want to go up a dimension and imagine some sort of one-parameter family of surfaces, of things undergoing surgery. So this is a cutaway. Let's imagine I have a red ring that's really hot. And I turn it on for a little while, and then the air near the ring is very hot, and as I move away, it's cooler. And I can look at the place where the temperature is some fixed number. I can look at isothermal surfaces. So in this case, the yellow surface is isothermal. It's got the shape of a donut. And that blue surface is where things are a little cooler is isothermal. And that has sort of the shape of something like an apple. And as I move out, as I sort of looked at the isothermal surfaces that went from being really hot to being cool, that isothermal surface is going to undergo a transformation, which is the fundamental transformation of surgery. And I've tried to put some pictures up. I don't know that I was so successful, but so I used control panel to say I'm thinking about the moduli space. So G mod PL is over there on the left, and that green dot is a point on it where I'm looking at that donut-shaped surface. Now, I think this slide transition didn't work out very well. I want to zoom in and just look at a cutaway, just a piece of that donut, not the whole thing. And what happens as I change the temperature, I move somewhere in that parameter space, G mod PL, and a ring forms around the middle of that surface, and it gets cut. And as I move a little further away, discs get sewn in, and now I change its color because it's cooler, and then remember that was just a little piece of the surface, and now I have a piece. If I sew the outside back in, or I zoom out, I'm at the other piece. So if I ran it backwards, I have this, it's being cut in the middle. Oh, that's not running it backwards. I made a mistake. Anyway, was supposed to get us back to this. So that's the basic maneuver of surgery, and it's what you would see if you were studying isothermal surfaces as I was looking at various temperatures. Okay, so there's this. So let me go back to this multiverse picture, where and just put together the kinds of geometry we've been led to think about by sort of going through the history of the study of geometry. So there was our world and the Platonic abstract forms, but then when we thought about geometry as being like the positions of the knobs in a control panel or something else, we came upon these other notions of smoothness and piecewise linear, notions of proximity, notions of how things transform. And then when we want to study those abstract notions themselves, sitting above it is what's called a homotopy type. And one of those homotopy types, G mod PL, is the moduli space. It's the thing that controls all the relationships in the box below. And that's the thing that Dennis undertook to study. Okay, well, so now I'm kind of done with the math part, and I can finally get down to the legend of the great, wild, manifold rodeo. Yeah, we're ready. So So the Great Wild Manifold Rodeo. This was back in about 1966 at a secret rodeo ground somewhere in Texas. It was a group of cowhands and riders that used to meet and do daring feats of riding on wild horses. So this day in 66, it was a hot day. There was not a cloud in the sky. The only thing in the sky was buzzards circling around, waiting for someone to have a tragic fall off a horse. It was a dangerous rodeo. So the morning started out. Milner took the reins. He rode something called the Hauptvermutung, trying to control manifolds. And he rode for a little while, and he discovered two PL manifolds he discovered a counterexample to the Hauptvermutung, and he fell off the horse at the end. And then, I got so nervous that you weren't laughing earlier, I kind of lost the thread of all this. So, and I was so confident I didn't write it down. So, all right, yeah, okay, here we go. So then Kerver came along riding a horse with a brand PL, and he discovered PL manifolds that didn't have smooth structures, and then he fell off the horse. And Milner and Kerver, they did some very exotic maneuvers that we called spherical, discovering exotic spheres, and they eventually fell off the horse again. Browder came riding in on a horse called Surgery, did quite a few rounds, seemed to really have that horse under control, but he couldn't handle all the problems it threw at him, and then Browder fell down. And then there was a lull. And this shadowy figure moved in, took off his hat, and it was Dennis Sullivan. So they brought in a horse for Dennis to ride, and it just wasn't good. He just shook his head and said no. And so no one knew what to do, and he pointed in the distance where there was this dark barn. And people were shaking their heads. They didn't want to know what was in the barn. And so the managers, they went and they got this beast. And it wasn't an ordinary horse. It was some beast from a different thread in the multiverse that was only a homotopy type. When you looked at it, it just seemed to keep changing forms. And you couldn't even figure out how to get on it, much less control it. And right on the side of that transforming beast was the brand Gmod PL. So Dennis hopped up on Gmod PL and he started riding around, and it was looking bad. It was an interesting ride, but it was kind of going on and on. Looked like he was going to get thrown off. He stayed on it, and the managers were worried that the audience wouldn't be entertained enough, and even the buzzards were getting bored. And so they had the rodeo clowns come out and start throwing some barrels on the field, and the horse started going towards one of these barrels, and without seeing it, and Steenrod in the audience said, "Hey, look out, there's an obstruction there." And Dennis said, "Don't worry, I got this. I can see all the obstructions." But the horse lurched, and it started going to another one, and Steenrod yelled out, "Just so you can see all the obstructions, that's not good enough. What are you going to do about those obstructions?" And so Dennis gave a sly look. There seemed to be kind of a change in the light, and the horse reared up because it took note of all these obstructions and threw Dennis up into the air. And he was holding onto the reins with one hand and his feet off the ground, and with a light, fantastic toe, he landed on the saddle on just one foot. And then it was as if the whole field got fractured like light through a prism. There was a whole bunch of horses, and they had labels. One of them was called 2, one of them was called 3, one of them was labeled 5. They were labeled after the prime numbers for some reason. Another one was labeled Q, which either stood for the inventor guy in the James Bond movies, or maybe the rational numbers. But there were infinitely many of these horses, and Dennis was riding them all, but they were like a lot littler than the original one, and he could tame them all, and he tamed them all, and never got thrown off. So he's riding around and around and around, and nothing is stopping these horses because the barrels have set up these like continuity channels between them. And there was a group of rough riders, a rough gang of riders from a nearby farm that went by the name the Galwa group. And they wanted to get in on the action. So they came in and they busted up all the barrels and made the path really discontinuous, and then the whole ride settled down. So that is the true story of this famous Sullivan ride at the Great Wild Manifold Rodeo. And it's, and that's, yeah. Sorry, so I have to, there we go, okay. All right, well, that's what it felt like. I don't know. That's what it felt like to us, that when you came in and studied Dennis's work, when I came on the scene, it was as if it was all happened at this just crazy, wild, legendary event. Let me just take a minute here to talk about what the actual innovations were. So there was a famous paper, the famous MIT notes, which were notes Dennis wrote up about his analysis of Gmod PL. And these were something you couldn't get hold of. When I was a student, the older people talked about these MIT notes. You'd find reference to them in papers, but they weren't, that you just couldn't get hold of them. You'd hear a rumor that somebody had a Xerox copy or they would have lost it. And it eventually got republished by Andrew Rudnitsky a few years back, and now it's something you can download illegally and read if you want. And in this paper, so the material of that paper, what was available to us, were a couple of famous papers. So this one, I just love the title, which was called The Genetics of Homotopy Theory and the Adams Conjecture. And in this paper, I mean, it's worth it just to read the first paragraph. Dennis was an extremely eloquent writer, and he also wrote sort of purposefully. He wrote about abstract mathematics, and it was all in service of a remarkable relationship between different purposes. And this one, The Genetics of Homotopy Theory, was an amazing paper. I studied it very hard as a student. And one of the things in there was a factorization of homotopy types in terms of prime numbers. It's like the prime factorization of an integer. And that was a really influential piece of work, and those of us who work in homotopy theory use that all the time, this sort of fracturing into primes, localization. This is just part of the standard picture in homotopy theory now, but it had huge influence in its day. He studied an action of the Galois group on the profinite completion of spaces. He was able to solve something called the Adams conjecture, and the way Dennis wrote about it, it was the miracle of discontinuous maps. He could produce transformations on a homotopy type that we still have no way of understanding in any other terms, and that led to a number of new problems and new solutions in the world of algebraic topology. This paper, Infinitesimal Computations in Topology, had to do with this relation between smoothness and piecewise linear and trying to import some of the notions of smoothness into the piecewise linear world. And it also had a tremendous influence. It set up this enormous industry of what's called rational homotopy theory that people still study today. And one of the things that it let Dennis express was things up to finite ambiguity. So a lot of these parameter spaces, they have finiteness in them. And if you're willing to look at things up to finite ambiguity, then there's an easier problem you could try to solve, a more complete statement you could try to make, and it gets located in this world of rational homotopy theory. And one of the things I find really striking, especially in the context of this story, is that he showed that the homotopy automorphism group of a finite homotopy type is defined by algebraic equations. So if you remember the arc of my lecture, right after, as we moved out of the Plato, the Euclidean geometry, into more modern geometry, we passed through things that were defined by algebraic equations, like the Kummer surface. But it was a long way. It was several other layers of abstraction from that to get to homotopy types. And yet Dennis showed that the automorphism groups of those are defined by algebraic equations. It's sort of, it's an amazing, it's kind of an unreasonably precise structure that's occurring at the level of homotopy types. So in my world, I came into the subject in the late 70s and the early 80s, and Dennis had left, and he'd gone into dynamical systems. And then in the late 90s and the early 2000s, or I guess it was in the 2000s, he and Moira Chaz introduced this notion of string topology. And this was very exciting. We were all really excited to have Dennis participating in topology again, and these ideas were very provocative and very, very influential. And in the context of the ideas we can talk about, it's like you're not probing a space by points, but you're probing a space by circles. So instead of going out and doing a survey of a landscape and standing at a point and making some measurements, you've got some big loop of string and you're looking at what it does when it's laid down on the ground at various points. And these circles transform through surfaces, through surgery, in fact, and harnessing this kind of geometry is a very exciting thing to topologists, and it had a lot of influence and continues to, and it led to deep innovations in the interaction of topology and physics. So I don't know, I wasn't told in advance who was actually going to be in the audience. Usually when you give a talk like this, people say, oh, it's a completely general audience. These are just going to be people that wandered in from the street. But it turns out that the only people that really wander in from the street are mathematicians. So your talk goes to a bunch of I'm giving a talk to a general audience of mathematicians who are pretending to be a general audience. But just in case you were a member of a general audience, then a lay person, as we say in math, I might have given you the impression that Dennis Sullivan is getting the Abel Prize because he rode a horse that was beamed in from a different thread of the multiverse longer than anybody else. And that's not quite true. So Dennis left topology for about 15 years and went into dynamical systems. He's also getting the Abel Prize for the work he did in dynamical systems. And that's the subject of Etienne's talk this afternoon, and I'm very much looking forward to learning about that. All right, that's it.